Hello, welcome back to Keystone Tutoring. And today we are talking about utilizing functions to solve problems. So, if you are in the New South Wales syllabus, this is from the 2017 syllabus, but I believe it is also used in the new upcoming 2024 syllabus. It's the point is use the concepts of functions and relations to model, analyze, and solve practical problems for Maths Advanced Year 11. So we'll be going through this, and pretty much what we'll be doing today is going through these four topics here: financial mathematics, radioactive decay function, finding functions through graphs, and finally a practice question which sort of utilizes all aspects from the previous three questions. So what we'll be talking about first is we'll be given functions and then we'll be sort of dissecting them, dissecting these functions to sort of get them into, rearrange them into the way which the question is asking us. That will most probably be seen within here and here. Finding functions through graphs, we will be given graphs and therefore find the corresponding function, and the practice question will incorporate all three. So let's get straight into it. So the first one we'll be talking about financial mathematics. So we're going to be considering the case. So Ron, our person here, has $100 today, and he wants to determine the interest rate he needs to receive back in order to have $130 in exactly 5 years' time. So what is this question asking us? If we break it down here, we know he has today $100. In 5 years, he wants $130 in exactly 5 years. So, and then if we look at the formula given to us, ST equals 100, bracket 1 plus R, bracket to the power of T. So we know ST. ST is the money we have at T time years. So here S of 5 is ours, and that will be 130. S of 0 is just equal to the 100, the money we want today. T, as stated here, is 5 years' time. Therefore, the only unknown we have here is our R, our interest rate. So if we look here, this is just a bit of a diagram schematic of this. $100 today from the bank in 5 years, he wishes to have 130. So what we want to do is rearrange this formula to get it in terms of R. So let's do that with the actual subbing in of the numerical values. So 130 is our money we want in 5 years. 100 is the money we have today. 1 plus R to the power of 5. I think maybe it's not important to note for year 11, but just a side note that this formula here is a discrete interest rate. So that means money is compounded at specific time periods and not continuously. Just a little side note. So what do we want to do to get it in terms of R? We want to make R by itself. So first we'll see, what can we do? That's 130 divided by 100 each side. Hundreds cancel out. We have 130 on 100 here, which is equal to the 1 plus R to the power of 5. If we have a 5 here and we want to get rid of it from here, what we do is we flip this power to the other side, but we just do 1 over 5. For example, let me just give you an illustration. If this was squared, it would simply be, let's just say it was 1 plus R squared equals X, for example. Um, that's simply, in another way you would see it, is just equal to the square root of X, which is just equal to X to the power of 1 on 2. So this here is just X to the power, 1 plus R to the power of 1 on 5 is, yeah, we just put it, sorry, um, lost my train of thought there, but yes, that would be just 1 on 2. So just for clarification's sake. And then finally, we have the 1 plus R, so we can obviously bring the minus 1 to the other side. And when we put this into the calculator, we see that Ron would require an interest rate of 5.39% per year. Why do we say per year here? Because T is in terms of years. If it was in terms of months, it would be a different story. But yes, so we need an interest rate of 0.0539 per year in order to have that exactly $100 in 3 years' time. Awesome. So that is this example done. Now let's go on to the radioactive decay example. So, what is radioactive carbon? This is just a bit of a science lesson, a bit of a plus. It's an unstable isotope of carbon, which pretty much means it's radioactive and therefore is dangerous. It can cause cancer and things like that. So, if there's a radioactive spill in an area, let's say at a power plant, there's a bit of a radioactive spill, you obviously want to evacuate that area in order to not expose anyone to it. But we also have to think, how long would it be until we can actually go back into this area where all the radiation is gone? A famous example could be Chernobyl. When that radioactive spill happened, there is still very high concentrations of radiation there today. In some areas of Chernobyl, it is still unsafe to visit. So you want to think, how long can we go back until we can go back into this area and not be exposed to dangerous levels of radiation where it's safe? So in this one, we're going to be talking about radioactive carbon. So there was a spill. And we want to know, how long would it take in time that there's only 25% of that unstable carbon, that radioactive carbon left in that area. And we are given the fact that RT, the amount of radioactive carbon remaining, is equal to E to the power of minus K times T. K here is ln over 2, so this is the radioactive decay constant for radioactive carbon, and this will always, if you're ever given a question like this will be given to you, not expected. Awesome. So let's think about the information we have. RT represents like the percentage amount of radioactive carbon left over. So when the initial spill happened, what would that be? That would be 100%, or if you want to put it in terms of a number, just equal to 1. And then therefore at the same time, T would equal 0 and K would always be as it is. Awesome. So if we want to know the time left until 25% of that carbon, that means that RT should be 25%, or as we can see here, 0.25. So we have RT, we have E, obviously E is always E, and we have K given here. So the only unknown is T, and therefore we'll just rearrange the equation. Simply anything zero point 0.2 with an E just becomes ln, and then the E drops off, and then the power of the exponential just goes down like this. So we have ln of 0.25 minus ln of 2. So then I did ln of 2 divided ln of 0.25 divided by ln of 2 here. When you plug that into the calculator, you receive a number of -2. And what remained was minus 1 over 5 is 5,730 times t, times each side by 5,730, and we find that the amount of time until 25% of that carbon left would be 11,460 years. So a very long time, and you probably wouldn't want to visit an area like that for the foreseeable future. Awesome. So now we come to determining functions through graphs. We're going to start and only do a very simple example in this video here today, as this is just an introduction. We're going to be thinking the linear case. So the question asks, given the graph below, determine the function of this graph. As it is linear, we automatically, it's a very simple case, come to the equation of y equals mx plus b. Y being the y-intercept, m being the gradient, x being the x-intercept, and b is just another constant. So what is the y-intercept? The y-intercept is the point where the line crosses the y-axis, and at this case, it is +3. The x-intercept is the point where the line crosses the x-axis, and as we can see here, it is -5. So in order to determine our function, y equals mx plus b, we consider the two situations. What happens when x is equal to 0? So when x is equal to 0, we have the y-intercept 3 is equal m times 0 plus b. Awesome. So then when x is equal to 0, we are on this line here, just for clarification's sake. When x is equal to 0, that means this is only here, so it has to be on this line. And on this line, we know y is equal to 3. So we have m times 0 plus b, so therefore we get b must equal to 3. The second case is what happens when y is equal to 0. When y is equal to 0, it must be on this line here, must be on the x-axis. And when it's on the x-axis, we know that x is equal to -5. So we have 0 equals mx plus b. So therefore, 0 equals mx times -5 plus 3, which is equal to 0, and we got that 3 from the B from the line above. So we know -5 equals -3, taking that 3 to the other side, and therefore m equals 3 on 5. And therefore our equation we get is y equals 3 on 5, x plus 3, and that is our final equation. Awesome. So now it's our final example. We're going to bring all of this together. So the question says we're in a taxi and the initial charge is $3. So as soon as we step in, we're charged $3. And for every kilometer driven, we are charged an additional $2.5. So first is find the function which represents the price charged for a journey which traveled j kilometers. Okay, you may be thinking, what does this mean? It's quite simple. It's finding the function f bracket, we traveled j kilometers in this case, j. So this is what we've got to find. So let's break down the question. Even if j is equal to 0 and we just stepped in the taxi and stepped out, we'd be charged $3. Therefore, there has to be a 3 in this equation. So we add 3. But that's only initially we're charged $3. And then for every extra kilometer driven, every extra j kilometer, we're charged $2.5. So let's say j was equal to 1 in this case. What would it be? Would we have $3 plus 2.5? Would have $5.5 for this journey charged. Awesome. So therefore, what would we do? We would add a 2.5, but what would we times it by? This is the important part. The important part here is we times it by j, because as we said before, this is for every extra kilometer traveled. So simply, that is the equation we have. Now we have a question. If we were charged $25 for our fare, how many kilometers did we travel? So what is that asking us? So as what function does this represent? This represents the price we were charged. So therefore, we know this from question 2. We know this to be 25. And it's saying how many kilometers did we travel? And in our function above, j is the number of kilometers. Therefore, we want to change this function and get it in terms of j. So let's do that now. We have 25 is equal to 3 plus 2.5 j. Awesome. So let's rearrange this. What's 25 minus 3? Simply put, is 22. And then that is equal still to 2.5j. And then finally, we just divide each side by 2.5. So j is equal to 22 on 2.5 kilometers traveled. So that is the number of kilometers we have traveled, 22 on 2.5. Now, simply put, the question is asking us to sketch the function, so the graph. So let's do this here. Going back to our previous page, remember we had a linear function and had this y-intercept, x-intercept gradient, and the constant, which is equal to. So let's consider the case where f of j is equal to 0. When f of j is equal to 0, equals 0, we have 0 equals 3 plus 2.5j. So j being our x-intercept, and I might just make that a bit more clear here. So this is our j, and this is our f of j here. Just rearranging that simply, we get j is equal to -3 on 2.5. Awesome. So we just took the 3 to this side, which would become a negative, and then just divided each side by 2.5. So that is around here, -3 on 2.5, a bit bigger than 1, a bit bigger than -1, sorry. Awesome. So now let's see the case when j is equal to 0. When j is equal to 0, f of j becomes, we have f of j, f of 0 is a better more accurate description, is equal to 3 plus 2.5 times 0, which anything times 0 is 0, so we get 3. Awesome. So now we know our y-intercept, our f of j is 3, and therefore we can sketch the function as a straight line, just like that. Awesome. So that comes to the end of the lesson. Thank you very much for watching, and I wish you the best of luck in your studies.